In this problem, our task is to approximate the integral from 0 to 2 e to the negative x squared over 2 dx. And we have to use numeric methods because we cannot compute the precise value of this integral using the fundamental theorem of calculus. This is so because the function e to the negative x squared over 2 does not have an antiderivative that we could express in terms of elementary functions, that is, in terms of functions with which we can compute. Therefore, numeric methods are the only possible methods to approximate the value of this integral. We need to estimate the errors, and our task is also to understand which methods work best for this particular integral. To estimate this integral from 0 to 2 e to the negative x squared over 2 dx, numerically we first observe that in the interval of integration, that is when x is between 0 and 2, the graph of this function, that is the red curve shown here on the right, is decreasing. So the function is decreasing, and this means that right n approximation is a lower bound for the value of this integral, and left n approximations are upper bounds for all values of n. So for any n, right n is less than or equal to the value of the integral, and that is less than or equal to left n. Computing with a calculator or computer, we get that right 10 is approximately 1.109 and left 10 is approximately 1.282, and the value of the integral lies between these bounds. But the difference of these bounds is 0.173, so we can say only that the value of the integral is between these bounds, but the error may be rather large. It is bounded by the difference of these bounds, which is 0.173. We need to use better methods. To that end, recall what has been discussed in the lecture on numeric integration. So if the graph of a function is concave up, then when we approximate the value of the integral with the midpoint approximation, then we consider rectangles like the one shown here. Its height is given by the value of the function at the midpoint of this particular subinterval, which is the base of this rectangle. Now take the upper side of this rectangle and rotate it about its midpoint. We get a polygon that lies completely below the graph of this function. When we have done this rotation, then we have added something to the original rectangle and taken away something. We have added the green triangle and taken away the red triangle. But these have the same area. Therefore this area of this polygon that lies completely below the graph of this function is the same as the area of the original rectangle. And therefore we know that mid-n approximations are less than the value of the integral. Likewise, trapezoidal approximations give values which are larger than the value of the integral by this picture shown here on the right. So we conclude that if the graph is concave up, then mid-n is at most the integral from a to b f of x dx, and this is at most trapezoidal approximation n for all values of n. And these mid and trap approximations are better than left and right approximations. So we observe that the function f, which was e to the negative x squared over 2, we differentiate it twice. We get that the second derivative is x squared times e to the negative x squared over 2 minus e to the negative x squared over 2. And this is positive when the absolute value of x is larger than 1, and negative when the absolute value of x is less than 1. It is 0 when x is 1 or negative 1. So we conclude that the graph is concave down when x is between -1 and 1, and concave up when x is larger than 1 or less than -1. And this means, by the previous observations, that when we apply the trapezoidal approximation on the interval from 0 to 1 to this particular integral, and midpoint approximation on the interval from 1 to 2, we get a lower bound. And this lower bound is much better than the original lower bound that we got. So likewise, the midpoint approximation applied to this particular integral between 0 and 1, and the trapezoidal approximation applied in the interval from 1 to 2, the sum of these two approximations gives us an upper bound for this particular integral, and computing with n equals 10, we get 1.1956 is less than or equal to the integral from 0 to 2, either negative x squared over 2 dx, and this is less than or equal to 1.1968. So the approximation is that this is approximately 1.1962, and computation with a computer algebra system yields even more accurate estimate, but it shows that what we got using midpoint and trapezoidal estimates is already pretty good, 1.1962. So here, to get to these better approximations, we needed to figure out the direction of concavity of the graph of the function, and then use the midpoint and the trapezoidal approximations accordingly.